All right, so the plan for projectile motion is I've given you the 7 types on the board. We're going to go through this sort of handout today. We may or may not get to some sample questions today. Really, all there is like sort of 3 sets of notes, and then there's a couple labs on projectile motion. They're a lot of fun. Okay, so we'll probably be having a test relatively soon. I would estimate end of next week. Okay, so earlier we discussed the vector quantities, velocity, and acceleration. Since only horizontal and vertical motion was considered, we did not need to know about vector addition or the techniques of vector resolution. But for objects projected at angles other than straight up or straight down, we do. And you guys already know how to add vectors, so it shouldn't be a problem. A projectile is any object that is projected by some means and continues in motion by its own inertia. Cannonball shot from a cannon, a stone thrown into the air, or a ball that rolls off the edge of the table are all considered projectiles. These projectiles follow curved paths that at first seem rather complicated. However, these paths are surprisingly simple when we look at the horizontal and vertical components of the motion separately. And that is, my friends, the key. The horizontal and the vertical components, you separate them. Okay? And they are independent of each other. The horizontal motion of a component of motion for a projectile is no more complex than the horizontal motion of a bowling ball, rolling freely along a level bowling alley. If the retarding effect of friction can be ignored, the bowling ball moves at a constant velocity. It covers, like if friction can be the slowing down of friction, right? You ignore friction, it slows it down.
So if you toss that whole unit out the window.
Yeah, exactly. It covers equal distances and equal intervals of time. It rolls of its own inertia, with no component of force acting in its direction of motion. It rolls without accelerating. The horizontal part of a projectile's motion is just like the bowling ball's motion along an alley. Here's a picture here, right? These bowling balls are equally spaced, which indicates constant horizontal motion, right? Roll a ball along a level surface and its velocity is constant because no component of gravity acts horizontally. Drop it and it accelerates downward and covers greater vertical distances each second. The distances are increasing here. Interestingly enough, the horizontal component of motion for projectile is completely independent of the vertical component of motion. Put a star beside that or underline it or what have you, because that's pretty important. The horizontal and vertical components are independent. Their combined effects produce the variety of curved paths that projectiles follow.
This is a paragraph that we have.
Oh yeah? Is it on the next page?
Wait, go back for a second.
I'm missing something? You're right, I think I am missing something. There's a vertical component of motion, right? Yeah. I think it's more or less covered it. All right, the multiple flash exposure of figure 2 shows equally timed successive positions for a ball rolled off a horizontal table. Investigate the photo carefully. There's a lot of good physics there. The curved path of the ball is best analyzed by considering the horizontal and vertical components of motion separately. There are 2 important things to notice. The first is that the ball's horizontal component of motion doesn't change as the falling ball moves sideways. The ball travels the same horizontal distance in equal times between each flash. Let me just draw a line here and show you. Okay, so like in other words, if I go with the back of the ball, okay, and I put it right there, right, to right there, to right there. All those distances between those lines are going to be the same. It travels the same distance to the right every time. How come? It's moving at a constant speed horizontally. There is no force causing it to do what? Accelerate, speed up, or slow down. Now, having said that, we all know there is air resistance, and it is going to slow down, right? If you've ever golfed before, you know that the ball eventually reaches a point where it just sort of drops, right? Especially in the wind. Okay, so the first is that the ball's horizontal component of motion doesn't change if the falling ball moves sideways. The ball travels the same horizontal distance in equal times between each flash. That's because there's no component of gravitational force acting horizontally. Gravity acts only downward. So the only acceleration of the ball is downward. The second thing to note in the photo is that the vertical positions become farther apart with time. The distances traveled vertically are the same as if the ball were simply dropped. You can see here, I'm going to draw in red this time. properties, let's make it red. Okay, so if I see, do you see how this ball, excuse me, lines up with that ball? And if I make another, how this ball here lines up with this one right here. The ball that's been projected sideways is in exactly the same position vertically as if it were just dropped. How come? Because vertical and horizontal components are independent. Let me show you one last one. Right, this one here. Same exact position. How come?
Not really are.
Gravity is accelerating them equally at minus 9.8, right? They're going to be at exactly the same spots vertically, regardless. Okay? So the downward motion of the ball is the same as that of free fall. The path traced by a projectile that accelerates only in the vertical direction while moving at constant horizontal velocity is called a parabola. When air resistance can be neglected, usually for slow-moving projectiles or ones very heavy compared to the force of air resistance, the curved paths are parabolic. Okay, so here's the first question. At the instant a horizontally held rifle is fired over a level range, a bullet held at the side of the rifle is released and dropped to the ground. Which bullet, the one fired downrange or the one dropped from the rest, strikes the ground first? Is it on the sheet? Yeah, so here's my rifle, right? And I've got a bullet that is fired like this and then drops, and I've got another bullet that drops like that. Which one hits the ground first?
One going straight down.
Well, answer. Go ahead.
Oh, it's on.
Yeah. Go ahead and answer. Is it A, the drop bullet, the fired bullet, the same one, same time, or could be either one?
Well, we've been talking the whole time at the same time.
That's correct, Mike. We have been talking about that.
Say it over and over. It's the
So
same
he's
time.
talking about the bullet drop, it's just the bullet or the bullet with the casing?
The same, good question actually. The same object that's being projected. Mike's going to go with the same. Has anyone seen the Mythbusters episode on this? Come on, Alex, answer the question.
Is one on this type of question?
There is.
Watch the question.
I believe that's what this link is.
We were watching it last week. It was on the slide for friction.
Correct answer should be collecting results. Takes a while.
100%.
Should be 100%, yes. The correct answer is C, the same time. Okay? Some classes I have a hard time convincing people of that, right? Although the video definitely helps now. They believe Mythbusters. They don't believe me, they believe Mythbusters. All right, let's move on. So what if it's going upwards? Not sure what I do with my sheets anyway. Oh, here we go. Consider a cannonball shot at an upward angle. Pretend for a moment that there is no gravity. And then according to the law of inertia, the cannonball will follow the straight line path shown by the dashed line in figure 3. So if you shot a cannon and there was no gravity, what would it do? It would just travel in a straight line upward at the same angle, right? But there is gravity, so this doesn't happen. What really happens is that the cannonball continually falls beneath this imaginary line until it finally strikes the ground. Get this, the vertical distance it falls beneath any point on the dashed line is the same distance it would fall if it were dropped from rest and had been falling for the same amount of time. So in other words, if you drop a cannonball from right there, it's going to fall exactly 5 meters. And if you drop a cannonball from right there, in 2 seconds it would fall exactly 20 meters. And if you drop a cannonball from there and let it fall for 3 seconds, it would drop exactly 45 meters.
And this is all because
Oh, physics
vertical and horizontal.
are independent, exactly. The gravity is pulling it down, right? And it doesn't matter, gravity doesn't care, Jimmy crack corn, how fast it's going sideways, right? It falls at, it accelerates at minus 9.8.
Smoke crack corn?
Is that a formula we should know there?
Get this, the vertical distance, okay, I did this, right? This distance is given by d equals 1/2 gt squared. You've seen that formula before. Where have you seen 1/2 gt squared? I'll write it in the form that you might remember it at.
80 squared.
D equals VIT plus 1/2 AT squared. How come the VIT has disappeared?
Yes.
Because the vertical component is 0. If I were to drop it, the initial vertical component is 0 if I were to drop it, right? It doesn't matter that it has an initial horizontal component. The initial vertical component is 0 if I drop it. Velocity. Well, the component of velocity. Okay? We can put this another way. Shoot a projectile skyward at some angle and pretend there is no gravity. After so many seconds t, it should be at a certain point along a straight line path. But because of gravity, it isn't. Where is it? The answer is it's directly below the point. How far below? 5t squared. Or more accurately, 4.9, 1/2 of 9.8. Note another thing from figure 3. The cannonball moves equal horizontal distances in equal time intervals. This distance from there to there is the same as from there to there, and is the same as there to there. How come? Because the vertical component is constant, provided that there's no friction. Okay? No acceleration takes place horizontally. The only acceleration is vertically in the direction of Earth gravity. The vertical distance it falls below the imaginary straight line path during equal time intervals continually increases with time. Figure 4 shows vectors representing both horizontal and vertical components of velocity for a projectile following a parabolic path. Notice that the horizontal component is everywhere the same, and only the vertical component changes. Note that the actual velocity is represented by the vector that forms the diagonal of the rectangle formed by the vector components. At the top of the path, the vertical component vanishes to 0. Let me put the vertical in blue. There's the vertical. There's the vertical. The vertical here is 0. There's the vertical. There's the vertical. Let me put the horizontal in red. In fact, the reds are always what? Always equal. Only the horizontal changes. And so the overall resultant is the sum of those two, right? That one's 0, so it's there. Does that make sense?
Wait, what did you say about the sum of the black one?
The black one is like the overall velocity is equal to the vertical velocity, right? Plus the horizontal velocity. Okay? But the VH stays the same. At the top of the path, the vertical component vanishes to 0, so the actual velocity there is the horizontal component of velocity at all other points. Everywhere else, the magnitude of velocity is greater, just as the diagonal of a rectangle is greater than either side. Figure 5 shows the path traced by a projectile with the same launch speed at a steeper angle. Same launch speed, different angle. Notice that the initial velocity vector has a greater vertical component than when the projection angle is less. This greater vertical component results in a higher path. Why does it go higher up? Well, because it has a higher vertical component. It takes longer for it to go to 0. The horizontal component is less, so the range is less. When I say the range, what does that mean?
Just on the top.
No, it means the horizontal distance. Yes, you were. Range means the horizontal distance. Could you fire it at more than one angle for it to land at the same spot?
Yes, you could. Yeah, with like different means. Yeah, it depends on how much force is behind it.
Figure 6 shows the paths of several projectiles all having the same initial speed but different projection angles. The figure neglects the effects of air resistance, so the paths are all parabolas. Notice that the projectiles reach different altitudes. That's this one here, Mike. Right? That's referred to as the altitude, or heights above the ground. They also have different horizontal ranges or distance traveled horizontally. The remarkable thing to note from figure 6 is that the same range is obtained from two different projecting angles, angles that add up to 90. An object thrown into the air at an angle of 60 degrees, for example, will have the same range as if it were thrown at the same speed at an angle of 30 degrees. Okay? They land at the same place because the angles are complements, add up to 90. Which one's in the air longer? The 60, the blue one, right? It takes longer, but how come it ends up at the same spot? How can that be? Which one has the greater horizontal component here? This one has the large vertical horizontal component. This one has the smaller one. So how can, if they're traveling different speeds, how can they end up at the same spot? This one's got the small time, and this one's got the bigger time. And they're complements of each other, right? Big T times little VH is equal to little t times big VH.
How are you doing?
What angle should you then launch to retain maximum range? Maximum range is attained when the ball is batted at an angle of nearly 45 degrees. In cases where the weight of the projectile is comparable to the applied force, as like a heavy javelin is thrown, the applied force does not produce the same speed for different projectile angles, and maximum range occurs for angles quite a bit less than 45 degrees. So if it's something fairly heavy, right, you actually want less than 45 degrees. Okay, it's because the applied force does not produce the same speed based on their masses. So the 45 is sort of for a optimal object that you're launching. We've emphasized the special case of projectile motion without air resistance. When there is air resistance, the range of a projectile is somewhat shorter and is not a true parabola. If you've ever golfed, you know that when you hit a nice high ball like that, eventually it sort of just drops down like that, right? That's how those guys hit the green and make it stop. If it was traveling on a parabola, it would do what? It would bounce and run. Okay, so they hit it high so that it lands, they call it landing soft, right? In other words, it's coming straight down. It has no horizontal component, so it doesn't fall off the green. Am I right?
Yeah.
Can I do it? No.
Have you ever got a hole in one before?
If you're chipping over the sand trap, what do you do?
You hit the sand.
No, if you're trying to get it over the sand trap, right? You hit it high, right? Especially if you're on a downslope or something like that, you want to hit it high and so that it lands close to the hole and just sort of sticks there, right? That's one way to do it. Or you hit it low and then you sort of run across, right?
Or you just get like a bogey, like halfway through the course, just give up and just drive around while Adrian like keeps going.
Okay, next question. Here's your question. A projectile is shot at an angle into the air. If air resistance is negligible, what is its downward acceleration?
It's not a plot, not like there, right? Negligible.
Yeah, that means there's no air resistance. What is its downward acceleration?
Oh, never mind. I can't find something.
I don't think so.
What are the,
You have to type in a number.
Interruption. Would all grade A students please report to the multipurpose room now, please?
what do you mean a number?
What is the numerical value of the downward acceleration?
Numerical value, well,
What is the horizontal acceleration of the same projectile? At an angle, yep, same one. Same. What is the horizontal acceleration? Correct answer is 0. The horizontal acceleration is 0. Horizontal acceleration. The words are right there. You can't tell me you didn't.
I didn't read that. I heard someone else say it.
It's really only 3 words long. Horizontal acceleration. 0.
Ah, you do that one. You do it.
Let's try this one. At what part of its path does a projectile have minimum speed, the smallest speed? Is it at the start? Is it at the end? Is it at the peak? Or is it the same speed throughout? There is no air resistance. Correct answer? Survey says? Correct answer is C, at the peak.
Oh, no.
Minimum speed. Why is it the minimum there at C?
Because that's where-
Remember, the horizontal is always the same, right? The vertical is the one that changes, and so this is the actual speed. So which one is the longest black arrow? Or sorry, which one is the shortest black arrow? At the peak. Why at the peak? Because the black arrow, the overall velocity, is equal to the blue horizontal component. That's where it's at its smallest speed.
I really mic'd up on that one.
Yeah?
I'm micing up on this guy.
If air resistance is small enough to be negligible, a projectile will rise to its maximum height in the same time it takes to fall from that height to the ground. That is because its deceleration by gravity while going up is the same as the acceleration by gravity while coming down. The speed it loses while going up is therefore the same as the speed it gains while coming down. The projectile will rise to the ground with the same speed it had when projected from the ground. This is only true if what? If it lands at the same vertical height as which it was projected. What if it's off a cliff? Is it traveling faster at the bottom than it is here? Yes. How come? More time to accelerate here, right? In fact, how fast is it going right there compared to right there? Exactly the same. Because it's just as much speed as it's lost on the way up, it's gained on the way down. If an object is projected fast enough so that its curvature matches the curvature of the Earth, and it's above the atmosphere so that air resistance does not affect its motion, it will fall all the way around the Earth and become an Earth satellite, right? And you may have seen this in grade 11, I can't remember. Imagine if I'm on top of a really tall mountain and I throw a tennis ball, right? It's going to do this, right? And eventually I'm going to be able to throw it so fast that it does what? It literally falls all the way around. Hits me in the back of the head. Okay?
Did you know if you could do that? He shot something, it went all the way around.
Is this a story?
He shot it, and he's like, oh, wow, it closed it and killed me.
You see that on the Bugs Bunny cartoons all the time, right?
Pardon me, interruption with Joel first.